Okay, so I am here to help you with your college geometry homework, and so we're going to look at the homework that's due on Friday, and I'll try to give you guys some hints and help you do some of these problems. Okay, so on number one, what we want to do, let's pull this up and make sure it stays up. What we want to do here is use our plane separation axiom to prove this. So it says let L be a line and A, B, and C be points, and G not lying on the line. All right, so you can draw a picture of this. It's probably a good way to start the problem. So number one, I have a line L, and then I have A, B, and C points that don't lie on L, and I want to prove that if A and B are on opposite sides, so I have A up here, and then I have B down here, and of course they're on opposite sides. And then I have B and C are on the same side, right? So C's on the same side, right? The obvious conclusion, right? So I have these points here, and I know these points here. The obvious conclusion is that A and C are on opposite sides, but I want to prove it, and the hint is, use B4. So the proof of this, right? So to prove this, what am I going to do? Well, I'm going to assume what's given, so I'll start there. So assume A and B are on opposite sides, so OPP, opposite sides of L, and B and C are on the same side of L. Right. Then I'd say, want to show. What do I want to show? Well, I want to show that A and C are on the same sides of L. All right, so I want to show A and C are on, did I say same? I meant opposite, right? A and C are on the opposite sides of L, or on the opposite. So let's just say OPP again. All right. And I'm sure there are lots of ways to prove this, but I think the simplest is just do it by contradiction. So suppose not. Right? So suppose not. Right? I.e., that is A and C are on the same side. Right? And so what you want to realize here is what we actually have. If you assume A and C are on the same side, right, we know this, B and C are on the same side, and so we can call up, let me pull this up for you so you can see it, and pull this down. Right, so behind here we can pull this up, and we can then use the plane separation property, because it says if A and C are on the same side and C and A are on the same side, right, then we know that B and A are on the same side, or A and B. It doesn't matter which way you say it. All right, so suppose not, that is A and C are on the same side, and so we know, all right, so we have A and C on the same side, so we know that B and C, or you can say also C, well, so we know B and C are on the same side. All right, so thus, we know C and B, that's terrible, let's erase that. Let's switch back to red. I like red better. So the C and B are on the same side. And if you want to say because sidedness is reflexive, you can, right? But you don't have to, right? So on the same side of L, but you can state that. But I think it's pretty clear. Thus A and B are on the same side. Again, let's make that clear. Same side of L. And that's by, and let's just say B4, right? Plane separation property 2, so B4, 1, sorry, B4, 1. Right? But this contradicts, right? So of course this, but this contradicts A and B on opposite sides. All right, so therefore, what do we know? Well, we know that then therefore A and C, right, are on opposite sides. Our assumption was incorrect then, that A and C are on the same side. So we know now that A and C are on opposite sides of L, and that's what we wanted to show here. So we wanted to show that A and C are on opposite sides of L. All right, so moving on to number 2. And so in number 2, what you want to show is you want to show that every line bounds exactly 2 half planes, and these half planes have no point in common. And so the statement before this is telling us what a half plane is. And a half plane, what it is it's these equivalence classes that come from the sidedness relation we defined in the last homework. And so I put down the definition of the equivalence class. Remember, we say in this case right now, A is equivalent to B if and only if A is equal to B, or the line segment AB intersect this line L is equal to the empty set. So this is already given to you. The line is always given to you, and so and you can draw a picture of it. So here's L. What does it mean for A to be on the same side of B or related to B? It means you have A over here. Here's B. When you connect the dots, right, the line segment doesn't go through the line L. Then we call when we say that they are on the same side. All right. So, but how do we prove that every line bounds exactly 2 half planes, and these half planes have no point in common? All right. So we could write this down. All right. So every line bounds exactly 2 half planes that have no points in common. Let's say that have no points in common. All right, so proof. So just let L be a line. And so I have my line L, and then I want to show that there exists half planes, and so then by, all right, the idea is this, by, and we can kind of, let's get rid of this. All right, so the idea is I have my L right here, and then I know, let's do a different color, I know there's going to exist a point A off of L. I think this is proposition 2.3. And then I know there also exists a point P on L, okay, and that's proposition, oh, not proposition, but axiom I2. Okay, so I have 2.3 gives me a point off, I2 gives me a point on, and then of course I know there exists a point here, so all three of these lie on the same line, B, right, by B2. B2. And this point has the property that A star P, that P lies between A and B. All right, so just write that up. Right, what I said in blue, write it up. So by 2.3, there exists a point A that lies off the line. By I2, there exists a point on the line. And by B2, there exists a point P such that P is between A and B. And then once you have that, you have your setup. Because my claim is this. My claim is if you look at the two half planes, the half plane containing A and the half plane containing B, they don't turn out to be equal. They actually turn out to be not equal, because you can kind of see from the picture A and B should be on opposite sides, and they are. Okay, a number of ways to show this. Right, you can say, notice that A B bar intersect L actually equals, well, we don't even need to say equals, let's just say, so notice P is an element of AB, line segment AB intersect L. Since, let's say, what do we have? A star P star B, and P an element of L. All right, so this tells me obviously it's in the line segment, right? And this tells me it's in L, so it's in the intersection. All right, so notice this, thus A is not on the same side as B. So I drew the equivalence relation with a slash through it, right? And so that tells me that the equivalence classes are not equal. So thus, hence, HA is not equal to HB. And I also know, as sort of like a little freebie, the equivalence classes are disjoint, so is equal to the empty set, since they are equivalence classes. So that's a real nice little property of equivalence classes. And so we know we have at least two half planes that are not the same, and we want to show there exists exactly two. And so the way this works is now we're going to just let C be any point in the space, take out L, of course, because we want to consider the points on the line, and we want to show, well, what do we want to show? We want to show that either HC equals H sub A, or the half plane containing C equals the half plane containing B. All right, so suppose now, B and C are on the same side. Right. Then we know that B is related to C because the relation sidedness, and we have H, the plane containing the hyperplane containing hyperplane. The half plane containing B is equal to the half plane containing C. And so we're all done with that part. So now suppose B and C are on opposite sides. Right? So if they're not on the same side, they're on opposite sides. So now suppose B and C are on opposite sides. So what you need to notice here is that B and C are on opposite sides, right? But what else? If we go back up here, what are we assuming about A and B, right? Because H of A is not equal to H and B, right? What do we know? Well, so suppose B and C are on opposite sides. And then let's do red again. So suppose B and C are C. Now we know what? A and B are also on opposite sides. Because the half plane containing A is not equal to the half plane containing B, right? Which means that A and B are not on the same side. Because if they're on the same side, they'd have the same equivalence classes. All right, so we have this nice little statement here. So hopefully you can see an A and B are on opposite sides. And we know something. If A and B are on opposite sides and B and C are on opposite sides, what can we conclude? All right, so thus we can conclude, right, A and B are on opposite sides, B and C are on opposite sides, A and C are on the same side, are on the same side of L, right? By B4 by B4 part 2. All right. Hence, let's go back to red. Hence, we know that the half plane containing A is equal to the half plane containing C. All right. So therefore, we either know the half plane containing C is the half plane containing A, or the half plane containing C is equal to the half plane containing B. So therefore, basically, we've shown every line bounds exactly to half planes that have no points in common. Okay. And now let's take a look at the next problem. So number 3, which is sort of a long one, but it should go really fast. All right, so on number 3, what you need to do is you need to try to understand this new relation. So the new relation says here we take a point in S, be a point on a line L. So let's draw a picture. And so we talked about this a little bit today in class. So this is the idea of line separation. So we have this L, and we take a point P on it. And then we're going to take two other points, A and B, which are different from P. So you have A and you have B. And we're going to say A is related to B if and only if A is equal to B, or what? Well, the line segment AB, right, P is not in the line segment AB. Right, this is what we mean by A and B being on the same side of P. So basically, we define this relation, and then, if A is related to B, we say A and B are on the same side of P. Whereas if A is not related to B, then A and B are on opposite sides of P. We want to draw a picture of each part below. So this is the line separation property. We haven't really proved it yet, but we've basically done all the work. So when you come to class on Friday, I'll talk for just a brief moment about it. But we've already done all the work, and it says this, you know, if A and B fall on the same side, and B and C fall on the same side, then A and C, of course, fall on the same side. So you want to draw this picture. And then you can do part 2, which says if A and B are on opposite sides and B and C are on opposite sides, then draw the picture that demonstrates, that shows that A and C should be on the same side of B. All right, so that's not too bad. So I think part A, you guys can probably hack out and do on your own. And part B really isn't that bad either. So on part B, what you're going to do is you're going to show that this relation here, this means a sidedness with respect to P really, is an equivalence relation. And so, you know, you're going to show the reflexive property. So all you need to do is say, you know, let A be a point on the line L different from P. And then, of course, you know that A is equal to A, which obviously implies A is on the same side. A and A are on the same side of B. All right, and then part C, you're going to assume A is related to B. All right, so then what do you know? Well, then you know either A is equal to B or P is not an element of the line segment AB. If this, right, then B is equal to A, and you get B is on the same side of A. If this, all right, then you know P is also not an element of the line segment BA, because these two things are equal. We've shown that, so you can just use it. Right, now that we've proved it's true, I don't really think you need to cite anything here. I think we can just say it's obvious from now on because we've already shown it's true. And so if P is not an element of the line segment BA, then again we know B is on the same side of A. And then finally, for part D, oh, I'm sorry. These are 1, 2, and 3. That's where I'm getting confused. This is 1, this is 2, and then this is 3. The transitive property is the simplest of them all in a sense, because what does this say? Just read it. It says A is on the same, A and B are on the same side of P. B and C are on the same side of P. We want to show that this implies A and C are on the same side of P. But that's just the first statement of the line separation property. So you just say, assume this, then by the line separation property part 1, A and C are on the same side. And you're all done. All right. And then flip over the page and you have part C. On part C, what do we need to do? All right, so let's talk about this one. All right, so that last part, easy if you just use a line separation property. So now I'm going to make these equivalence classes. So we consider this equivalence class, which we call the half line. All right, so these are all the points on the line, not including P, right, such that A and B are on the same side of P. All right, so if you draw a picture of this, which we can do, what this is really sort of telling us, then we can use, and then let's suppose A is over here. That little h sub A, let's use a different color. So what does little h sub A represent? It represents all the points over here on this side of P. Right? Of course, it doesn't include P, right? Like a hole here, right? But all these points on this side. And we want to prove that every point on a line bounds exactly 2 half lines, and these half lines have no points in common. All right, so I'm not going to copy down the statement, but the proof is very similar to the one we did for the half plane. So when I prove this, what you want to do is you just say, okay, let P be a point on a line L. Okay, and so you have this line L, and you have a point on it, right? How do you find the point A? Right? You can just set it up. Hey, by what? By I2, All right, what do we know? We know there is a different point A on L. All right, so easy enough. And then by B2, we're going to get another point, which we'll call B. All right, so this is B2, this is I2, and we're basically almost done here in a sense, right? So by B2, there is a point B on L with what? With P between B and A. Okay, and now my claim is this. My first claim is that, oops, not capital H, I want to show little h. So my claim is that the half line containing B is not equal to the half line containing A. Right, and how am I going to show this? I mean, there are actually lots of ways. What you can say is just notice what? Notice P is an element of AB bar, right? Since P is between BA, which implies P is between AB by not B2 but B1. By B1. Alright, so thus these two half lines are not equal. And we even know that their intersection then is empty. Because they are equivalence classes. Period. All right, so now we want to show that, so we know they're not equal, we know they don't intersect, and so now we want to show that these are the only two. So again, just like before with the half planes, we let C, but we let C be on the line, but not P. And we want to show that either the half line is equal to C is equal to the half line containing A, or the half line containing C is equal to the half line containing B. All right, so suppose, and this is the same way that we did last time, and so I'm not going to finish it off. You can look at the proof we did for the half plane, but you're going to suppose that C and A are on the same side. Or you can do C and B. I guess last time we did C and B. So suppose C and B are on the same side. Then we know that these half lines are the same. Okay, by definition, right? C is related to B, so these half lines have to be the same. Now suppose C and B are not on the same side, right? That means that C and B are on opposite sides, right? So now suppose C and B are on opposite sides. Right? And then you want to say something like, notice that B and A are also on opposite sides. Right? And that follows from this. Right? So let's get a different color here so we can just kind of talk about this. All right, so then you want to write something like, notice A or B and A are on opposite sides because of this. Right? And now we know C and B are on opposite sides, B and A are on opposite sides. And so we can call up by line separation property 2. Right? What do we know? We know C and A are on the same side. Right, and then so this tells us that the half line containing C is equal to the half line containing A. And so then we can write, therefore, every point on a line bounds exactly two half lines that don't have any points in common. All right, to finish this up, you're going to prove essentially the same statement you proved in number 1, but instead of doing it for half planes, right, for sidedness with lines, you're going to do it for sidedness with points. And it's exactly the same proof, right? And you're going to do it by contradiction, and you're going to show it violates one of those line separation properties I gave you in class. All right, so try that one, and hopefully this video will help you. All right, so I'll see you guys tomorrow.